So isobutyric acid smells like rancid butter. It was pretty bad. This is one of the old IRs that I had taken. And as usual, folks, you should always look at the functional groups in the structure you're looking at. Go back to the Pavia book in the IR section. Look up alkane structure in this case, as well as carboxylic acid. So clearly, carboxylic acid, there's got to be some kind of OH stretch, and you'll tell by the reference spectra that is in Pavia. You're going to have a large structure, which is the whole thing here. This whole vast blob is part of the OH stretch of a carboxylic acid. Students in the past used to actually do a baseline correction on this line. This is not baseline. It's part of the overall OH stretch of a carboxylic acid. This peak here that's shooting through the top, we have to be a little bit careful. Whenever you're running a carboxylic acid, sometimes these little tiny peaks on top of the mountain can be part of the OH stretch. There's no way to guarantee whether that 2978 little peak is part of the alkane CH sp3 CH stretch or not. So basically on this one, I would just say, look, this is part of a carboxylic acid OH stretch. Then we move on to the carbonyl C double bond O stretch. So 1705 is obviously that one. Outside of that, I mean, there's no aromatic functional group. It's only alkane. So some of this stuff in particular right here could be called a CH bend if you really wanted to. The 1241, I'm not sure what that is, but if you can see it assigned in the Pavia book, you could. Thionyl chloride. Now, the reason why we have to take an IR of this one is because we know we distill some of this off in our first fraction, if there's any left. So it's nice to know if there's a definitive peak that belongs to thionyl chloride. And you can see very much it has one monstrous peak for itself. We don't actually have to label exactly what that one is. And to be quite honest, I'm guessing it could be an S double bond O stretch, but I have no idea for sure. All we're using this for is a means of looking for leftover thionyl chloride in your product. Do you see a big 1228 type peak? So, the product, isobutyryl chloride. Again, now clearly you can see there's no more carboxylic acid OH stretch, that mound, you don't see that. You see peaks here just under 3000. All of these are carbon sp3 hydrogen stretches. You go to the carbonyl of acid chlorides, and you can see that clearly there's two peaks, 1770, 1808. Both of those are part of the C double bond O stretch. If you went over to Pavia and we look up acid chlorides, and we'll look at a couple examples. Here's a very simple one. You can see right around 1800 they labeled the 1. Let's look at a different example. Now they show you can often see 2. They're going to call it Fermi resonance, but the point is it's conjugated. Well, conjugated in their sense. Ours is not conjugated. Conjugated means that your carbonyl is conjugated resonance with a ring. But the point is this is a C double bond O stretch of an acid chloride. So we'll go back here and we're okay to label that. What else is left to label? I mean, you could say a few of these things here are CH bend if you really wanted to. Now this is a peak at 1235. Is that the same as the 1228 peak? Is it possible for it to shift a little bit? So folks, it's interesting whether or not we want to prove whether that 1235 was actually leftover thionyl chloride in this case, or let's look further up here. Notice how there's no, unless that would be higher. See 1235? And then this is 943, but I don't see any other evidence of a clear-cut 1228 peak. But what we could do, and you can mention this in the discussion, you don't have to mention it right on this one, this could be rerun, this exact same sample. You could spike it with a little thionyl chloride and rerun the IR and wait to see if you see the appearance of another 1228 peak just to the left of this one, or does this one get bigger? That'd be one way to prove it. Move on to NMRs. And instead of stopping this recording, I'll just keep moving around, or I'll set this down for a second. I'm going to actually write the structure. I've written it on many lab reports. It's a rule. You must draw a picture of the structure on every single spectra. So that's what I'm doing right now, just to make sure I don't get caught, lose marks for myself. A little bit messy maybe. This could be a mixture, as it will be. And then we'll go through that. All right. So isobutyric acid, we'll run an NMR. I'll back up a bit here. I should have posted this. I think I did. If not, you can definitely see it here. Try and find a reference one. Way out at 12, worth almost 1. You can see a peak from the hydrogen of the carboxylic acid. You can see what should be a septet, which is coming from the 1 hydrogen right there. The 2 methyl groups are identical. There's 6 of those hydrogens on methyl, talking to 1 right there. Therefore, it should be a doublet. And sure enough, there's the doublet. And you can see that the carboxylic acid is around 1.1-ish. The reason why I'm focusing on that is if we shift over to your product, you're going to get the exact same look of your starting material, a doublet and a septet. But let's look at that doublet. The doublet itself is shifted slightly to the left. So instead of 1.1, it's 1.36, 1.2, and even the septet is shifted. This one's out to like 3.3. 2.9 is kind of the center. The starting material, 2.4, is the center. So obviously, the septet of the starting material and the doublet are a little more left compared to your product. C13, you expect to see the carbonyl carbon, that carbon right there in the middle, and then the 2 methyl groups. So that obviously the 2 methyl groups is this one. This one, which is occurring at 33, has to be from that carbon. And then out at, now this one says 183. Don't forget, folks, this was run by a student on the isobutyric acid, but in any event, it should match 183 for the starting material. There's that peak. If we go to the carbon of the product, and this is a students that ran it, so again, I'm assuming that they had their TMS or their reference peak done pretty well. 177, 178, you'll see that. And you go this way, just under 50, you're going to see the carbon right there. The 2 methyl groups will be the tall one. So what we did also is, I have one here, I don't think I posted it, but this is for your discussion-based knowledge. Why did I put both on here? Is because last year, I had a couple students run an NMR of the leftover liquid that was in the distilling flask down at the bottom. So sure enough, even though we don't see an obvious OH, carboxylic acid hydrogen down here at 12, when you go over this way, boy, that looks more than just a septet, doesn't it? And then when you look at the doublets, clearly you see 1 tall doublet, and then bedded down in there is a smaller doublet. So clearly the tall one here is the leftover starting material, some undistilled product, isobutyryl chloride, and this is an overlap. The taller one, septet, belongs to the starting material, and we know it's further left, and then slightly more to the right, see the lower lying ones there, that comes from the product. So clear as day, folks, there is definitely a mixture of both product and starting material in the flask. So this could be used for some discussion, and we'll follow up on that.